So as mentioned in the last lesson that we can use the table of standard reduction potentials if the reaction that we're looking at occurs at standard conditions, 25 degrees Celsius, 1 molar solutions of 1 molar concentration of solutions, and 1 atmosphere pressure for gases. Well, what if you have a reaction, a redox reaction that occurs in a galvanic cell or electrolytic cell that is not at those conditions? Well, we're going to apply something called the Nernst equation to determine non-standard potential difference and non-standard conditions. So here's one form of it. There's a couple actually. So we have E equals E naught minus all kinds of stuff. So our non-standard potential, so potential difference at non-standard conditions is E. E naught, of course, is at standard conditions. Ideal gas constant. Uh-oh, I forgot a couple things here. Let's fix this. Sorry about that. 2.303 times RT times natural log of Q. There we go. So R is our ideal gas constant. Of course, T is the Kelvin temperature. N is the number of electrons transferred during a redox reaction, or if we're just looking at one half reaction, the number of electrons involved in that half reaction. Of course, F is Faraday's constant. We can use 3 sig figs if you want, 96,500 coulombs per mole of electrons. And then Q is the reaction quotient. So that is one form. If we take 2.303 and R and F, we can combine all of those to get one number. We get a more practical derivation. So I believe you have both of these on your equation sheet. So this one seems to be a little more useful. This time we have log base 10, not natural log. And then this is only for reactions that occur at 25 degrees Celsius or 298 Kelvin. So let's suppose just the concentrations of the solutions are not 1 molar, then we can use this form. Of course, if the temperature is not 25 degrees Celsius, then we have to use the first equation. So something to keep in mind is how Q affects E and the relationship between the non-standard potential and the standard potential. So if Q is greater than 1, that means first of all we have more products than reactants, and kind of the reverse reaction is favored. Even though we have a one-way reaction, it is reversible, so it's really not at equilibrium, but we still look at the possible reverse of the reaction. If Q is greater than 1, that means the log will be positive, and that means then that the E is less than E naught. Of course, the opposite is also true. If Q is less than 1, where we have reactants favored, then the log of that will be negative, and E will be greater than E naught. So just some things to think about, especially when you're doing calculations. Make sure that your answers agree with your predictions. All right, let's take a look at example 817, example 21.5. So for this particular problem, we're just looking at one half reaction. So it says calculate the potential E for the iron 3, iron 2 electrode when the concentration of iron 2 is exactly 5 times that of iron 3. So take a look on the next page. So suppose you have in some half cell some inert electrode in a solution of both iron 3 and iron 2. Now we can look at the reduction, we can look at the oxidation, really doesn't matter. But since we use the table of reduction potentials, let's look at the reduction of iron 3 to iron 2. So the standard reduction potential is 0.771 volts. Now it says that the concentration of iron 2 is 5 times that of iron 3. So if we write our reduction half reaction, the iron 2 is the product. And so we're going to put iron 2 on top. Its concentration is 5 times that of iron 3. So if you want to give iron 3 a concentration of X, and iron 2 a concentration then would be 5X. And so then we have our Q is equal to 5. Plug that into the Nernst equation. Again, notice that Q is greater than 1, so that means our non-standard potential is going to be less than the standard potential, and we get 0.730 volts. Similar type problem here, so go ahead and do number 81 on page 836. That should be 836, I believe. Go ahead and pause the video. All right, so here's the setup. We have 2 moles of electrons being transferred. The standard half cell potential, that's a oxidation potential. Notice this is an oxidation reaction, is positive 0.28 volts. And then our Q is products over reactants. Cobalt is a solid, so we don't put anything on the bottom. And we take the log of 1.0 times 10 to the negative third, which is smaller than 1, which means that our non-standard potential will be higher than the standard potential. And we see that here we get 0.37 volts. All right, so go ahead and take a look at example 21.6. We'll start with that one on page 818. I'll read it to you. It says a cell is constructed at 25 degrees Celsius as follows. 1/2 cell consists of the iron 3, iron 2 couple, in which iron 3's concentration is 1.00 molar. Iron 2, 0.100 molar, and the other involves the permanganate manganese 2 couple in acidic solution, in which the concentration permanganate 1.00 times 10 to the negative second molar, manganese 2 1.00 times 10 to the negative fourth, and H plus concentration 1.00 times 10 to the negative third. Find the electrode potential for each half cell with these concentrations, and then calculate the overall cell potential. So I don't really like the approach that your book uses, even though it asks you to break it up into separate steps. So do like we did in the last problem, where you're finding just the non-standard reduction potential, and you'd find the non-standard oxidation potential, and then ultimately you would add those up to get the non-standard potential difference for the reaction. Another way we can do this is we can write the balance equation for the reaction, balance redox equation, as we see at the very end of the solution on the top of page 819, and then apply the Nernst equation just overall to that reaction. So we have our products are manganese 2 and iron 3, so we can take the concentrations of those, thinking about our Q expression here, those go on top, over concentrations of permanganates in iron 2 and hydrogen. Calculates Q, take the log of that. We first, of course, have to calculate the standard potential for the reaction using the values in the table. And so just a different approach. You can do it, for each half reaction first, find the non-standard potential, and then add those up to find the non-standard potential difference for the reaction, or you can just do it at the very end. We're going to not look so much at each individual half reaction. We're going to look at the overall reaction. And so I think starting off with the balanced redox equation for a reaction, calculating standard potential difference, and then applying the Nernst equation, calculate the non-standard potential difference. So let's do this. If you have some space at the very top of the page there, anywhere you have room, let's do number 87 on page 837. So we're going to apply this same reasoning here. And so what I want you to start off with is the balanced redox equation for the reaction. We'll just do letter A. Again, we have shorthand notation given to us here. So we have in 1/2 cell tin electrode in a tin 2 solution that has the concentration given to you there. And in the other half cell, we have a silver electrode in a solution of silver ions. So we need to determine first what substance is being oxidized, what substance is being reduced. We can do that using the table of reduction potentials. So I would compare Sn plus 2 to Ag plus. And what we're looking for is which one wants to be reduced more. And so the substance that wants to be reduced more is where the electrons are going to go. The electrons go towards the substance that wants to be reduced more. So let's do this. Let's break it up into steps. Use your table of reduction potentials, identify the ion that wants to be reduced more, pause the video, and then I'll tell you what it is, and then you can set up the problem. Go ahead and pause now. So it looks like Ag plus wants to be reduced more than Sn plus 2, so the electrons are going to go towards the silver electrode, so away from the tin and towards the silver electrode. So again, write the balanced redox equation for the reaction, calculates the standard potential difference first, using values straight from the table, and then apply the Nernst equation with the concentrations given to you in the problem to find the non-standard potential. Go ahead and pause the video and do that now. All right, so here's our setup. We have a balance equation here, the standard standard potential difference, 0.94 volts. We do log of Q for a Nernst equation, so concentration of, there we go, concentration of tin 2 over concentration of the silver. Looks like I did not square that though, so we need to square the concentration of the silver. So we might have to confirm my answer here and make sure that is correct, but that is our setup. Don't forget about your coefficients in your balance equation becoming exponents in your Q expression. So double check, that may or may not be the right answer. So hopefully it's something close to that. All right, next up, a little different problem. This time you are given the non-standard potential. Take a look in the table to determine the standard potential difference for this half reaction, and then we're solving for this time concentration. So go ahead and pause the video and work on that one now. All right, so here's our setup. The standard potential, reduction potential for silver is 0.80 volts. We're given the non-standard potential of 0.40 volts. And so we set it up like this. Notice my Q expression 1 over X for looking at this half reaction here, reduction of silver ions to silver metal. This is constant concentration, that's a solid, so we're going to do 1 over X to try to find the concentration of the silver ions, which happens to be 1.8 times 10 to the negative 7th molar. All right, so hopefully you already have an idea about the relationship between E naught and delta G. So here is the equation showing that relationship. And technically that's delta G naught. Number of moles of electrons gained, lost, transferred, however you want to look at it, is N. Faraday's constant once again. And then our standard potential measured in volts. Something to help you with the units. A volt is a joule per coulomb. So notice we have, delta G's in kilojoules or joules per mole. We got moles of electrons, Faraday's constant, coulombs per mole of electrons. And so in order for the units to work out, we can't plug in really volts for E naught. We need to plug in joules per coulomb. Ultimately, we're going to be left with joules or joules per mole. All right, take a look at 21.9. Read along. Calculate the standard Gibbs free energy change, delta G naught, in joules per mole at 25 degrees Celsius for the following reaction from standard electrode potentials. So there's our balanced redox equation. We use the values in our table to calculate E naught for the reaction, and then apply our equation here to calculate delta G. Notice in the equation we have 6 moles of electrons gained and 6 moles of electrons lost, or 6 moles of electrons transferred, so that is our N. And notice how the book does it here. We do 6 moles of electrons per mole of reaction. This way the units work out. Faraday's constants, notice it has been written to accommodate the units. So instead of changing volts to joules per coulomb, the book took the coulombs and converted that to joules per volt. So 96,500 joules per volts per mole of electrons. Multiply that by the standard potential difference, and we get our delta G. And notice something, E naught is positive, and so that should tell us something about the reaction. When E naught is positive, that means the reaction is spontaneous. And so our delta G should correspond with that. So notice delta G is negative. When delta G is negative, that again also means that the reaction is spontaneous. All right, next up, exercise 101 on page 837. Let's go ahead and just do letter A. Start off with the balanced redox equation for that reaction, zinc metal reacting with hydrochloric acid. And so, of course, chloride is a spectator ion. Use the values in the table of reduction potentials to calculate E naught for that reaction, and then use that to calculate delta G. Go ahead and pause and do that now. All right, so here's our setup, the balanced redox equation, our standard potential difference. We have 2 moles of electrons being transferred, so N is 2. Faraday's constant. And notice I changed the units from volts to joules per coulomb so that we're left with joules. Number was pretty big, so I converted that to kilojoules. So we end up with negative 147 kilojoules per mole. Again, which makes sense. Our E naught is positive, which means the reaction is spontaneous, so delta G should be negative. All right, one more equation. So here's got a couple forms for you. This is an equation showing the relationship between the equilibrium constant, this time K, and E naught. So if you take the natural log of K, set that equal to NF E naught over RT. That's one form of it. Another form looks like this. Instead of using natural log, we can use log base 10. Again, if we combine all of our constants, we can simplify it. Of course, this is if the temperature is 25 degrees Celsius. If the temperature is not 25 degrees Celsius, then we have to use the first form here. So K is our equilibrium constant. Again, N number of moles of electrons transferred. And once again, E naught is our standard potential difference. So again, this time something to look at is this relationship. If E naught is positive, what does that mean about the reaction? Well, the reaction is spontaneous in the forward direction where the products are favored. And so because of that, K should be greater than 1. And the opposite is also true. All right, take a look at the example on page 825 and read along with me. It says use the standard cell potential to calculate the value of the equilibrium constant at 25 degrees Celsius. So solution, we first calculate potential difference, 0.16 volts. Plug that in with all of our information. We have 2 moles of electrons transferred. This one is using the different form. I'm not sure why, but we could just use the form that has log base 10. And we end up with an equilibrium constant that has a value of 2.7 times 10 to the 5th. Again, notice our E naught is positive and K is big. It's bigger than 1. Also notice here, if you're going to use natural log, we need to take the inverse of natural log, which is E, of course. If you're taking the inverse of log base 10, that's your anti-log, or 10 to the x that you will use. All right, let's go ahead and try number 103 on page 837. Pause the video. All right, so according to our equation, we have 2 moles of electrons transferred. If you have a tough time seeing that, just take that equation apart, balance it, rebalance it, and see how many electrons are gained, how many electrons are lost. Our standard potential difference for that reaction is 0.54 volts. And we're going to take the inverse of log base 10 of both sides. And we end up with a K value of 1.8 times 10 to the 18th. Large value of K, again, which means products are favored, which again means that the reaction is spontaneous in the forward direction. All right, that concludes this lesson and this unit. Thanks for watching.